and start today's lecture. If throughout the lecture you can't hear me or need me to speak louder or have any questions, comments, or anything, just feel free to say it out loud or put it in the chat. Today, we're going to work on more reactions with alcohols. So this lecture is lecture 17. This is today's outline. We're going to start with a little bit of review, go into turning alcohols into alkyl halides. Then we're going to talk about epoxides and sulfides. This all may sound very foreign to you, but you guys are going to learn that today. So let's do a little bit of review at first. This is from Friday's lecture. Sydney went over this, so this might look familiar to you, but let's review it anyway in case you don't remember this. So we're going to review alcohol oxidation reactions. In that lecture, we talked about weak oxidation agents and strong oxidation agents and how they react with alcohol, essentially. So weak oxidation agents, if you guys remember, include PCC or pyridinium chlorochrome. I cannot say that, chlorochromate. It's a very long, hard word to say, so we just say PCC, right? Or DMP is also another weak oxidation agent. We also have strong oxidation agents such as potassium permanganate and different types of chromium species that Sydney mentioned on Friday's lecture that you guys might remember. So this chart right here that I made is essentially a summary of the different types of situations that you guys might encounter when it comes to alcohol oxidation reactions. So one of the situations, again, involves primary alcohols, as you guys can see here. And there's an example of primary alcohol right here. So if this were to be our starting material and we were to react it with a weak oxidant, then the weak oxidant product would be an aldehyde. You guys might remember that from Friday, right? But also with primary alcohols, there could be a situation where you have a strong oxidant and instead the product would be a carboxylic acid. So essentially the main point when it comes to this is that primary alcohols react differently when it comes to reacting with weak oxidants or strong oxidants. So with weak oxidants, primary alcohols will make or produce aldehyde, while with strong oxidants, they'll produce a carboxylic acid, such as shown here. So those are the two types of situations when it comes to primary alcohols. We have another situation that involves secondary alcohols. So here's an example of a starting material that is a secondary alcohol. So when it comes to how it reacts with weak oxidants or strong oxidants, it doesn't really matter. It reacts the same way. So whether it's a weak oxidant or a strong oxidant, it's gonna produce a ketone in either situation. So when it comes to secondary alcohols, the main point is that it doesn't matter whether it's weak oxidant or strong oxidant, it's gonna form a ketone, okay? And then another situation involves tertiary alcohols. So here's an example of a tertiary alcohol right here. If a tertiary alcohol reacts with weak oxidants or strong oxidants, it doesn't matter which one. Again, it's going to make no difference when it comes to tertiary as well. It's not going to react. So there's going to be no reaction, as you can see here. So these are all the types of situations you might see when it comes to alcohol oxidation reactions. Okay. Again, I mean, these might be different, right? But essentially it's the same deal here. If it's a primary alcohol, then there's two possible products where whether it's weak oxidant or strong oxidant, it's going to differ. But with secondary, whether it's weak or strong oxidant, there's not going to be a difference. It's going to form a ketone. And then tertiary, there's not going to be a reaction. Is there any questions on this slide right here? Anything I just talked about? Okay, cool. Let's move on to some practice on what I just talked about real quick. Let's start with question number 1 right here. So before we start, does anyone want to say what type of alcohol this is? Is it a primary, a secondary, or tertiary alcohol? Feel free, you can say it in the chat or out loud, whatever feels more comfortable to you. So we're looking at question number 1, what type of alcohol is this? Yeah, somebody said primary. Exactly, this is primary alcohol. Um, Sorry, that looks like a squiggle, but that is a one. So primary alcohol. And what type of oxidant are we working with? Is it a weak oxidant or is it a strong oxidant? Yeah, strong oxidant, exactly. Thank you for those of you that responded. So then in this case, if we're working with a primary alcohol and it's a strong oxidant, what type of product are we going to form? What is this alcohol going to turn into? Yes, carboxylic acid, exactly. So in this case, this alcohol is going to turn into carboxylic acid. So let me go draw that. Sorry, this is going to be a little bit wonky, but essentially it just turned into carboxylic acid. Is there any questions with this number, question number one? Any comments, concerns? Does this make sense to everyone? Okay, cool. So now let's look at question number two. Does anyone want to say what type of alcohol is this one right here? The secondary, exactly. What about the other one? What type of alcohol is the bottom alcohol? Primary, exactly. So this is secondary and primary. So in this question, they already gave us a product. What we need to do is figure out what type of oxidant would give us the product that is shown. So we're gonna have to analyze the product itself as well. So in this case, we can see that there's um, a ketone. We have an aldehyde right here. So let me just write the ketone, aldehyde, right? So essentially, the ketone really, the secondary, this one right here became the ketone, right? So that really doesn't tell us anything about what type of oxidant we want because we know whether it's weak or strong, it's going to give us a ketone. What we want to focus on is this primary one, right? To see if this reacts, what will give us an aldehyde. So somebody said a weak oxidant. You are correct. We would want a weak oxidant because that's going to give us um, this aldehyde right here. So does anyone want to give me an example of a weak oxidant? Yes, PCC. So PCC would be a good answer in this product or in this reaction right here. Does anyone have any questions on this? Okay, cool. So what about question three? We want to figure out what product it's going to form, right? So what do you guys think should be the product here? Is there going to be a product? Yeah, exactly. Some people say, is this even an alcohol? Exactly. There's no alcohol to react. So there's not going to be a reaction. So in this case, there's going to be no reaction. Or in other words, it's this product is going to stay the same. So I'm just going to go ahead and draw or redraw this. So it's just going to stay the same. Hopefully you guys can see that. But yeah, there's no change because there's no alcohol to be oxidized. So it's just going to stay the same. Is there any questions so far? So let's move on. Here are the answers so you guys can study later. Okay. So now we're going to go into turning alcohol into alkyl halides. And this should just say alkyl halide because essentially we're just going to be working with replacing the OH with a chloride, as you can see in this reaction right here. Okay. But first, let's focus on um, this part right here, right? So what is SOCO2? Let's kind of look at what that is. So SOCO2, this is the structure right here. Cyanochloride is what it's called essentially. Um, that is going to be a part of the reaction. We're going to see them in the mechanism. So let's kind of see, um, or yeah, just kind of like look at this product itself. So whenever you're doing a reaction, you might want to look at your starting material, right? And this is part of the starting material, just kind of to see what can react, right? Because if you guys remember, we talked about how when we're talking about electron density, and some atoms have more electron density than others, right? Because of electronegativity and like that stuff. So we want to analyze that because that can help us figure out what exactly is reacting, whether it's oxygen, chloride, or sulfur. So let's look at this molecule and kind of see what is happening. So we can see that sulfur right here has 3 very electronegative things surrounding it. So it has an oxygen right here and then chlorides. So essentially those 3 atoms are going to pull electron density away from sulfur and towards themselves. So they're going to be partially negative, while sulfur is partially positive. So that's a way to think about it. And looking at this, we can think, oh, maybe oxygen can give some of its electron density to somewhere else and react in that way. Or maybe the double bond, right? The double bond may also react. Or sulfur can, receive some electron density from another molecule. So it's good to analyze these molecules in that way. Okay, so we're going to talk more on that later. But first, let's look at the reaction itself. That's here in the bottom. We see an alcohol right here. In this case, it's a secondary alcohol. And we have SOCO2 right here and pyridine. So pyridine looks like this. And I just want to clarify that it's the same thing as, drawing is a little bit back. This is not any better. Essentially, it's just like this. Hopefully that, kind of like a benzene, but one of the carbons was replaced by N. So the circle just means that the double bonds, or the pi bonds are just moving around. Does that make sense? Hopefully I explained that well. But yeah, so I'm going to be drawing it in this way right here, but I just want to make sure no one's confused as I draw that these two are the same thing. Okay. So in this reaction, what essentially changed, right, between the reactants and the products is that OH was replaced by Cl, right? So let me write it down. OH replaced by Cl. And also there was inversion of stereochemistry, right? So the wedge is now a dash. So stereochemistry. So these are the main points in this reaction, right? So essentially OH is going to be replaced by Cl, and there's going to be inversion of stereochemistry. So we're going to look at the mechanism and see how this happens. First, I keep this products in mind as we do the mechanism, so it's easier for you to understand why things are happening. But this reaction may remind you of something, right? So what type of reaction do you think this is similar to? Like SN1, SN2, E1, E2? What does this remind you of? Feel free to say in the chat as well. Or out loud, however you feel. Yeah, some of you guys are saying SN2. So SN2, if you guys remember, it's kind of has a good leaving group. There's something attacking, doing a backside attack, and that kind of inverts the stereochemistry and replaces, something with something else. So it's kind of similar, right? So we'll see the mechanism in a moment, and you guys will be able to see how that happens. Although it's not really straightforward as an SN2 reaction, there's a little bit more steps because OH is not really a good leaving group. So we're going to be looking into that. Is there any questions so far? And this is just the main points, just written down in something more clear than my handwriting, essentially. So yeah, let's move on. So now we're going to start with the mechanism. And these are our starting materials. Again, we have our alcohol right here. We have our SOCO2 and our pyridine. I'm not drawing the pyridine until we need it because it's a little bit big, so we're just saving space here, but just know that the pyridine is what I showed you before. So again, we kind of want to analyze our starting products in terms of like electron density. Where is the electron density? Is there some partial positive, partial negative things going on here? we already analyzed this SOCO2, so I'm just going to go ahead and write what we came up with. We said the S was partially positive, and now let's analyze our alcohol. Alcohol is going to be partially negative, right, because oxygen is electronegative. So then it's going to pull electron density towards itself. And so this carbon is going to be positive because of the fact that oxygen is going to draw electron density towards itself. Is there any questions so far on this? Okay, so thinking about electron density, what do you guys think might happen? Feel free to see in the chat. What do you think might attack what? And it's okay to be wrong since you guys don't know the mechanism. But thinking about what is being formed and what kind of situation we have here, what do you guys think might happen? It's also okay to say that you don't know, then I'll just help you guys out. Yeah, okay, cool. Somebody said the O attacks the S, and that's exactly what happens. So one of the electron pairs right here in the oxygen, sorry, my arrow is a little bit wonky, but it's gonna attack this S right here. And okay, so if you guys notice now there's a bond being formed between that O and that S, right? And if you notice S already has 4 bonds around it, right? So we do this attack, right, where O is not being forming a bond with an S, then S will have 5 bonds. So we have to do something else to not disobey the octet rule, right? We still want to obey the octet rule. So what do you guys think will happen in order to avoid S having 5 bonds around it? Okay, someone said the CO leaves. That will be one of the next steps. There's something else that can happen that involves a double bond. So the double bond, so that's a big hit. The double bond, those electrons can go somewhere, and so we want to break a bond, right? So the double bond between S and O, between this right here, that double bond is going to go somewhere. Is it going to go to the S or to the O, right? Which one do we think is going to help the situation to avoid disobeying the octet rule? Yeah, someone said that this one right here is going to go up here. So that's exactly what's going to happen. Okay, so if we do that, then we avoid S disobeying the octet rule and still just have 4 things around it. So that's exactly what's going to happen. So let me erase that and show you guys what is formed. Okay, so we can see one of the pairs right here in the O attacks the S. This one, these electrons in the double bond will go to the O, forming this O minus right here. And we can see this bond that formed between these two. Okay, and then O right here has a positive charge because it already had 2 things attached, and now there's a third bond, which makes it positive. Is there any questions so far? Does this make sense to everyone? Okay, cool. So now we're thinking of we're trying to get to our products, right? So what can happen? What do you guys think might be possible to happen? Although this is a little bit difficult to guess. So just give it a go. It's okay if you're wrong. What is a step that can lead us towards a product? And if you don't know, just feel free to say, I don't know, and then I could help you guys out. And just a hint, it involves this negative charge right here. One of those electrons in the Okay, so somebody said, and they're correct, said that one of these electron pairs can come down here and form a double bond, which is what happens, right? But when that happens, then we would have 5 bonds around the S. So again, we want to avoid disabling the octet rule. So what would happen then is that the Cl will leave and take those electrons. So now S, next part, which is the product. So now, so that, let me just re-explain what I said again. So one of the electron pairs here goes between this bond to form a double bond. The Cl leaves as an ion, so you can see it right here. And this double bond was formed. But this is still attached to here, right? So now we have formed this right now. Is there any questions so far on what just happened? Okay, cool. So now we're closer to actually forming our products, right? So now, again, reminder that our product looked something like, it was a dash. Our product looks something like this, right? So in this step right here that we add, looking at this bottom right here, what might help us get to this? Now we have a CO that it's an ion, and we have, again, O is still partially negative, and this is still partially positive. So what can happen here in order to be able to form this? Involves the Cl, right? Exactly. Okay. Someone said the Cl attacks, does a backside attack in this carbon right here, causing this bond right here to break and those electrons to go to the oxygen. So now this oxygen leaves, but it's still attached to this. So all of this leaves together, right? And Cl came from the back, so now it's going to be this in this form right here. It's going to be dashed coming from the back, right? Does that make sense to everyone? So let's show how that looks like, right? Again, this left together. Oh no, I forgot an arrow. There's supposed to be. So those electrons left or moved to oxygen, and then oxygen left along with everything else. So now we see that right here. And then CO came from the back and kind of made that leaving group leave. So we just see CO as a dashed right here. Does that make sense to everyone? So now we have our product, right? Okay, so now we have our product, and that's good, but there's still other steps, because if you guys remember, or might not remember, from the first from the reaction that I showed you guys, one of the side products was SO2 gas, and we don't still have that product. So we have this, but that's not SO2, right? It looks close enough that it might be SO2, but it's not SO2. So we have to do more steps to kind of get there, but we did, in fact, already get the product that is important to us, which is this one, but there's still one more step in this reaction. Oh, yeah. Thank you for that question. So someone said, why is chlorine positive? This is supposed to be just a plus where I try to include all the products. So it's a plus as in kind of like a, you know what I mean? Hopefully that makes sense. So just like these are the starting materials, so I'm just trying to show that these are all there, not that they're positive. Yeah, thank you for that. Just to clarify to everyone, that's not a positive. Okay. So now the next step that we want to do is get to SO2, because that's also part of our uh, what's it called, our products, but not the important product that we want, which is this one, but we still have to take that other step. Uh, so now it's good to mention that this pyridine right here is a good base. So what's going to happen is that this is going to remove that H right there. These electrons from this between this bond right here are going to go to form a double bond right here between that. And then what's going to happen right again, once we form that double bond, if we don't remove another bond, there's going to be 5 bonds around it. So we have to make sure that something leaves. In this case, it's going to be the Cl right here. So now that will lead us to our SO2 product that we saw before. Let me just show that. You can see the SO2 right here that we formed. And this N, again, this just to reiterate, the pyridine looks like this. So whenever we add H, then that N has a positive charge. So that's why you see the positive charge right there. And then we have the chlorine that left. So you can see that right here. And then our final product that this is the one that's important to us, right? So yeah, this is how you get this product. Is there any questions on anything we just went through? And again, there's an arrow missing here. I'll add it to the slides before we post this. But yeah, is there any questions? Okay, yeah, another great question. So why is there an arrow next to the gas? So the arrow is also in the other slide. So essentially it just means that it's gonna kind of leave, the solution, essentially, because it's a gas, and the solution that we're working on is liquid. So it's liquid, so this gas is gonna leave the liquid. So essentially it just means it's gonna leave. Does that make sense? Hopefully that I answered that correctly. Okay, and then somebody else had another question. What does the final product of pyridine look like? So I can redraw it again. Try to draw it clearly this time. So it looks like this. And then so it has a positive charge because the N has 4 bonds. So it looks like this. Does anyone have any other questions? Yeah, so Cl's an ion with the pyridine. So that's why I drew it together. So you know how sometimes we draw NaCl because Na plus and minus their ions together. So that's kind of what's going to happen with the pyridine and Cl. Is there any other questions? I know there's a lot to digest, and we did a step by step. So just kind of feel free to, on your own time, go over this by yourself and try to think it. But yeah, is there any other questions? If not, let's do some practice problems. And this is just, again, the main point of this reaction, although we went through all that mechanism, is that Cl is replacing OH, and there's inversion of stereochemistry. Now let's do the practice problems. So looking at number 1 right here, we're looking at this right here. And again, OH replaces Cl. So what kind of product do you think this would look like? I kind of gave away the answer, but yeah. Is there going to be inversion of stereochemistry, tension of stereochemistry? Does stereochemistry matter in this question? This one's a hard one, so if you guys don't know, just feel free. You're like, I have no clue. Okay, so I'm just gonna go ahead and draw what happens. So essentially, it's just gonna replace OH. In this case, it's planar, right? So there's a double bond there. So stereochemistry is really not gonna matter that much in this question. What's just gonna happen is that there's gonna be, this is an O, by the way. It's just gonna be like this. Okay. Is there any questions? So this is a carboxylic acid right here. Yeah. There's no more questions. Yeah. So someone said this is a carboxylic acid, but does this still react like an alcohol? Yeah, so essentially just the same thing. OH is going to be replaced by Cl, but in this case, there's no inversion of stereochemistry because it is planar. So, any other questions? Okay, cool. Let's move on to question number 2. So this looks a lot more familiar to you guys than the other one did. So what do you guys think is going to happen? Somebody said it, so let me just go ahead and draw it. Essentially, it's just gonna look like this, right? The OH is going to be replaced by Cl. There's inversion of stereochemistry, so the dash is not going to look like a wedge, right? So it's going to look like this. Is there any questions? This is pretty straightforward. So, okay, if there's no more questions, and here are the answers again, if you guys want to practice later, but I'll leave it to Jen now.
All right, okay. All right, so I'm going to be talking today about two different kinds of molecules that we haven't seen before, but they actually have reactions that are very similar to the ones that we've already seen. So the first one, I'm going to talk about epoxides. This is going to be sort of a type of ether, and if you remember, that's going to be an oxygen connected to two acyl groups. And so these have a strain energy of 105 kilojoules per mole. And I know that number doesn't mean anything to you guys right now, but all you need to know is that this is going to be a very, very reactive molecule. And that makes sense because as we've seen, we haven't seen a lot of these kinds of like free atom molecules. Like we've talked about cyclopropanes before, but we haven't seen a lot of these kind of molecules because there's so much strain energy. And because of that, these molecules are going to be very, very reactive. So let's look at some of the reactions we can expect to see. So one of them is just gonna be ring opening. And this was going to be ring opening in a basic condition. And so this reaction is going to be an SN2 reaction, just like we've seen before, with one difference in that because this epoxide oxygen is going to be a leaving group, because of that, after this reaction is over, this leaving group, this oxygen isn't just going to float off on its own. It's still going to be connected to this molecule. It's just we're going to cut one of these bonds, either this one or this one of these bonds to a carbon, but the other one is going to stay there. And so the thing about this reaction is that it's both regioselective and stereoselective. And just to address any potential confusion, remember that regioselectivity, that has to do with the bonds that are formed. So whether the nucleophile, which electrophile is that nucleophile going to bond to? So in this case, we have two options, this carbon over here or this carbon over here. So regioselectivity is going to be which carbon that nucleophile binds to. And stereoselective is just going to be the spatial orientation of those bonds. So essentially, what angle is that nucleophile going to attack at? Is it going to attack from the bottom and make these two substituents go up? Or is it going to attack from the top, make these two substituents go down? So we've mentioned, as I said before, this reaction, we have this epoxide here, and our solvents or other reagents are going to be this solvent, this methyl alcohol. And we're going to have a catalytic amount of this base, this conjugate base. And when we say catalytic, it means that we only need a very, very small amount. And because if you remember from general chemistry, a catalyst is a reagent that appears both at the beginning of the reaction and at the end of the reaction. So it isn't used up. So once this catalytic amount of base is used for this reagent, we're going to regenerate it at the end so that it can go back and react with an unreacted epoxide and just continue doing this reaction over and over and over again. So we don't actually need the same amount of this catalytic base as we do epoxides. We just need a little bit, and that little bit can react with all of our epoxides. So as I said before, this is an SN2 reaction and it's regioselective. So can you guess where our nucleophile, in this case, it's going to be this catalytic base, where is it going to attack? Remember, we have two possibilities. This carbon over here and this carbon over here. These are two potential electrophiles. Can you guess which one is going to attack if this is an SN2 reaction? Exactly, the right carbon, because here we're going to have the least steric hindrance. And as you can see, this is going to be a tertiary carbon, and this is going to be a primary carbon. We don't count this oxygen, but yeah, essentially it's going to be the least steric hindrance here. And so it's going to attack from here. And because it's SN2, we also have that inversion of stereochemical configuration. Once again, it's going to attack from the bottom because it has to be anti from the leaving loop, which in this case is this oxygen. So it's going to attack from the bottom, and then this oxygen is going to be up here. So that's why I call it anti-addition. But remember, we're going to invert the stereochemistry at this carbon. So the product is going to look something like this. So as you can see, our nucleophile is going to attack here. It's going to attack from the bottom, and it's going to leave this epoxide up here, this epoxide oxygen, and that's going to have a hydrogen just to balance out that charge. I'll talk more about that later when I talk about the mechanism. But essentially, our product is going to look like this. So we see it's both regioselective and stereoselective. Okay, and so this is going to be the mechanism. I've drawn it here. So as you can see, this is our epoxide. I've only drawn the methyl substituents. And so as you can see, our catalytic base, the CH3O, is going to attack at the least crowded carbon. And because of that, because this carbon already has 4 bonds, because of those 2 hydrogens, it's going to have to kick off this epoxide oxygen. It's going to form this molecule. And because this oxygen is negative charge, we want to balance that out. So it's going to steal a hydrogen from our solvent, in this case, the conjugate acid of our base, so HOCH3. And because of that, we're going to be left with this final product. But also, as we see, we've regenerated that original base, that OCH3 minus. It's the same molecule that we started off with. And because we regenerated it, this molecule can go back and react with an unreacted epoxide and do this reaction all over again. So that's why we can just use a very, very small amount of base in order to run this entire reaction. Does anyone have any questions? Okay, I'll give you a quick second so you guys can finish up drawing this mechanism. But yeah, as you can see, keeping the stress is that it's both regioselective and stereoselective. But it's easy to remember just because this is just a regular SN2 reaction, that the same as we've seen before, just with the extra complication of that this leaving loop has 2 bonds to the molecule. Okay, and so I've stressed before that this is a basic condition. So obviously, what happens in an acidic condition? So what happens is that this epoxide is going to be much more reactive in acidic conditions for the same reason that OH is alcohols are more reactive in acidic conditions, because we can protonate this oxygen, becomes a much better leaving group. So this reaction here, it's going to have, we can use a similar solvent, just CH3OH, and now instead of catalytic base, we have catalytic H+, so like some catalytic amount of any strong acid or any acid. And so this reaction is also going to be regioselective and stereoselective. But it's going to be one complication. We would expect this to also attack from the least substituted carbon, but it actually doesn't occur. Instead, it actually attacks this carbon over here, which has the most substituents. But interestingly enough, it also still has inversion of stereochemistry. You're still going to have this nucleophile be on the opposite side of the bond from this leaving group, your epoxide oxygen. So I'm going to talk to the mechanism and explain why this happens. Okay, so this is what's happening. We have an original epoxide, the same epoxide as before, and this is going to be our protonated solvent. So it's CH3OH, but with an extra hydrogen from that H+ that was floating around. So this epoxide is going to steal that hydrogen. It's going to become protonated. And at this point, this is when a nucleophile attacks our most substituted carbon and then kicks off this oxygen. But why does this happen? So it has to do with the properties of this protonated epoxide. So this is actually a more accurate representation of exactly what's going on with epoxide. So essentially, when this epoxide oxygen becomes protonated, this bond over here between this carbon and this oxygen is actually very, very weak. And as you can see, that positive charge is going to be mostly centered on this oxygen here and this carbon here. But actually, most of our charge is going to be centered on this carbon. And because of that, this carbon almost acts like a carbocation. And it also, because of that, it also changes the shape of this molecule. So because this bond is very weak, these 3 bonds here are more like a planar orientation than like an actual tetrahedral. And so because of that, there's not going to be a lot of steric hindrance. There's a lot of room for a nucleophile to attack from the bottom. And because this acts like a carbocation, a nucleophile, it's going to act as like a very good electrophile. It's going to be very good for that nucleophile to attack it. And so that's why this nucleophile attacks this carbon. And as you can see, this reaction, as you can see, it's very similar to SN1, where your nucleophile is going to attack the most stable carbocation. But one major difference between this and SN1 is that you still have that inversion of stereochemistry. Because this is still a considered reaction, you still have to attack this nucleophile and at the same time kick off this leaving group. So this nucleophile still has to attack from the bottom, from the opposite side of this epoxide. And so because of that, we still have inversion of stereochemistry. So, so you can use SN1 and SN2 as a good way to remember the differences between basic and acidic conditions and ring opening. Just remember, you still have inversion of stereochemistry. And then as you continue this reaction, we have this nucleophile, it's still protonated. So we steal hydrogen from it, and then we take out that positive charge. And because of that, we've regenerated or protonated solvent. And because of that, this protonated solvent can go back and run this reaction all over again. We've regenerated our catalyst. Does anyone have any questions? Okay. If not, I have this slide that has a summary of what we just talked about. So we have this epoxide and we have two conditions, either basic or acidic, where we have the catalytic base or the catalytic hydrogen. And so when we have catalytic amount of base, the thing that controls a product is steric control. The nucleophile joins the less substituted carbon. And then when it's in acidic conditions, it's electronic control, where the nucleophile joins a preferred carbocation. So this is an SN2 reaction, and this is going to be an SN1-like reaction. It's not quite SN1, obviously, because we're not creating a carbocation substituent. It's not going to be inversion of stereochemistry, but it does. We can use that metaphor to predict a product. Okay. Does anyone have any questions in general about epoxides? All right. If not, I'm going to move on to our next molecule, which is sulfide. So sulfides, if you remember ethers before, it's very similar. So an ether is going to be an oxygen connected to two alkyl groups, and a sulfide is going to be a sulfur connected to two alkyl groups. We'll talk more about ethers on Friday, but essentially, if you remember, because oxygen and sulfur are on they have the same number of valence electrons, they have very similar electronic properties. So sulfurs and ethers have a lot of similarities, but one key difference is because sulfur, it's one group down, it's one period down. It's going to be a bigger molecule. It's going to be a bigger atom because of that extra shell of valence electrons. And so because it's going to be a bigger atom, it's going to form longer bonds, and those bonds are going to be weaker. And so one key difference between sulfides and ethers is that sulfides are less basic than ethers. And it's because a base, if you think about it, is going to want to form a bond with an oxygen, sorry, not an oxygen, a hydrogen. It's going to want to form a bond to a hydrogen and create a very stable product. And because that SH bond is going to be much weaker than an OH, sulfides are going to be less basic than ethers. That SH bond is going to be less favorable to form. And then just talk about some reactions to sulfides. So you can form sulfides in phenols. Phenols, if you remember, are going to be some alkyl group, sulfur, and then a hydrogen. And so you can make them as sulfides. And you can use this through the Williamson-Ether synthesis reaction. We're going to talk more about that once again on Friday, but you can use the exact same reaction for sulfides because they have very similar properties. So essentially, this reaction is going to be an SN2 reaction. So you're just going to have your alkyl halide as normal, but now your nucleophile, instead of going, in this case, your nucleophile is going to be a phenolate, which is the conjugate acid of a phenol, essentially just a deprotonated phenol. So you're going to use this deprotonated phenol as your nucleophile, and then you're just going to run a regular SN2 reaction. And so because of that, you're going to invert stereochemistry of just your alkyl halide. So remember to only invert the stereochemistry of your alkyl halide and not your phenol. The phenol, the alkyl halide here is not going to be affected. It's not really part of this reaction. But this is like the general reaction, like a general form of this reaction. So you have any phenols that are stands for any alkyl group. In this case, you're going to have your strong base. So NaH is is usually what you'll see, and you're going to be in some kind of solvent. In this case, ether is usually a sulfur. You see of it a lot. And so if you remember, this is going to be Na plus and H minus. And so this H minus here is going to take this H here, and it's going to form H2, which is, as you remember, a gas. And so because that's going to dissipate out of this reaction, leaving you just a deprotonated fuel and that Na+, that sodium plus, as a spectator ion. And so because of that, this RS minus that can act as a nucleophile or alkyl halide, it's going to replace that halogen with this RS and form R. And so just because I know a lot of you are visual learners, I'm just going to showing an example here. So this is going to be our fuel. Oh yeah, that was very fast. I can go back to this reaction and talk about it again. Hold on. Gotta hate PowerPoint. Actually, I'll just talk about it here because this is still the same reaction. So essentially we have a fuel that's going to be RSH. It's going to react with NaH and ether, which is our solvent. And so this hydrogen here, that's what's very important. That's going to be our H minus. That's going to be a very strong base. And so because of that, it's going to take this hydrogen from this fuel and form H2 gas. And because of the gas, it's just going to dissipate out of a reaction. So we don't care anymore. And we're also left with Na+. And so what we really care about is this fuelate, or the conjugate acid of a fuel. And so because it's just going to be this acyl group and then S minus charge, and because of that, this charge is going to act as a very good nucleophile. It can attack our alkyl halide. So in this case, I just have this Br and then 2 carbons. The upward arrow, that just means that this is going to be a gas. It's going to dissipate out of this reaction. So we use this upward arrow next to gases because of that, because remember, it's a gas. It's not going to stay in our container if we run this reaction. It's just going to dissipate out into the atmosphere, leaving just our liquids and our solids. So we just use this arrow to denote that it's going to go out of this reaction. It's not going to appear in later steps. And so because of that, we have our nucleophile, we have our alkyl halide. We can just run a regular SN2 reaction. It goes through the exact SN2 steps that we said before, so I'm not going to go into details, but this is going to be our end product. We have the original alkyl group that was connected to our sulfide, to our sulfur, and we also have the carbons that were connected originally to our halogen on the other side. So this is going to be a sulfide at the end. And if you remember, at this carbon, if this is a stereocenter, carbon on only this carbon, are we going to invert the stereochemistry because this is a SN2 reaction. For a nucleophile, that's going for the entire nucleophile, we're going to retain the configuration. So don't be confused and think that, oh, both the carbons next to this sulfur should invert the stereochemistry. It's just going to be this one. And if you remember your steps for the SN2 reaction, that will make sense. Okay, does anyone have any questions? Okay, if not, I'll move on to our next reaction. Oh, the bromine, that's from our alkyl halide. So remember, that's the halogen that was kicked off. That was our leaving group for this SN2 reaction. Any other questions? Okay. All right, and so our next reaction is fuel oxidation to disulfide. So a disulfide is going to be a sulfide just with 2 sulfurs instead. So it's going to be R, S, S, R. And we can do that by essentially linking 2 fuels together. So remember a fuel, that's going to be R, S, H. So we're going to link 2 of them together to form a disulfide. And to do that, we need Br2. So for a reaction, we're going to have, for every 1 mole of Br2, we need 2 moles of this fuel. And we're going to link them together and form HBr as our byproduct. And so this is what the reaction is going to look like. We have this fuel, and it's going to attack. It's going to form a bond between this Br, which is going to kick off this Br. This is going to be sort of like an SN2 reaction, but not quite, because we're not inverting the stereochemistry. But essentially, it's just going to be this this concerted nucleophilic attack and kicking off the leaving group. That's why it's SN2-like. And so I'm not going to deal with the mechanism of how this hydrogen gets kicked off, but essentially, you're going to form a bond between this R and S and then this Br. And at this point, this other fuel can attack this sulfur and then kick off this Br, this bromine. And at least with the end product of RSSR plus 2 HBr. The mechanism for this reaction isn't super important, but just like the beginning product and the end product are the very key points. This is how we link these two phenols, in order to form a double solid. Does anyone have any questions about this reaction? Yeah, and like one key thing is to conserve stereochemistry, because I said it was SN2-like, but it's not really an SN2 reaction. And so if these two acyl halides are stereocenters, we're not going to do anything with the configuration. So if you see these phenols and you see this reaction, you can literally just redraw those phenols just with those sulfurs connected. That would solve a problem like that on an exam. Okay, if there are no questions, I'm going to move on to a practice problem. So we're looking at this starting product. Can anyone tell me what kind of molecule this is? I've introduced two in my part of the lecture. So epoxides or sulfides. Those are your two options. Yeah, it's an epoxide because you have this oxygen in a free member ring. So even though we have this hexane, this cyclohexane here, this is still going to be an epoxide. Don't let that confuse you. And so we see our other reagents. We have this CH3OH solvent, and we have H2SO4. Does anyone remember what H2SO4 is? Yeah, it's an acid. And so we've learned two reactions for epoxides. We've had ring opening in basic conditions, and ring opening in acidic conditions. So because it's an acid, this is clearly going to be an epoxide ring opening in acidic conditions. Can anyone describe what a product is going to be from this epoxide with these reagents? And so remember, this reaction is both regioselective and stereoselective. So it's easy to start with the regioselective part. So for a nucleophile, which carbon is it going to attack? We have 6 options to choose from: 1, 2, 3, 4, 5, 6. Which number carbon is it going to attack? 1, 2, 3, 4, 5, 6. Now remember, is it going to attack the most substituted carbon in an epoxide or the least substituted carbon in an epoxide if this is the acidic condition? Exactly, the third carbon, because this is the least substituted carbon in an epoxide. I said these carbons just trick you out, but we're focusing on these 2 carbons here. So it's going to attack this carbon over here because it's the most substituted. Here, this one is a tertiary, this one is a secondary. So we're going to attack here. And so because of that, we're going to attack here. We're going to have to cleave off this bond between this carbon and this oxygen. And so we're going to form our end product. And as we said before, this is going to invert our stereochemistry. So that can be tricky to visualize with a ring. So I'm just going to show you, but this is going to be our end product. So as we see, our nucleophile attacks this carbon and it kicks off this epoxide. And so because of that, this epoxide is going to, this carbon over here is going to maintain its stereochemistry. It's going to look exactly how it's going to be the same here. If we were to do RNS, it would have the same RRS configuration, which is clear to see because this oxygen is going to be in front, this hydrogen back is the same here. But what happens in this carbon is that originally our biggest group, that oxygen, is in the front, and our smallest group, or the lowest priority group, is in the back, or highest priority group is in the front. And now suddenly our highest priority group is in the back, and our lowest priority group is in the front. So it's good to see that we have inversion of stereochemistry. So yeah, does anyone have any questions about this problem? I know I went through it kind of quickly. But yeah, essentially on an exam, it's very common to see rings just because that can trick you up. And it's also very easy to create stereocenters from those. But also remember that this reaction is both regioselective and stereoselective, and that can help guide your answer. Okay, does anyone have any questions? If not, this is all the material I had for today, so you guys are free to leave. if you guys have any additional questions, feel free to stay behind and Ashley and I can answer them. But if not, have a very nice Wednesday. Thank you guys so much for coming today.
Thank you.
Thank you.